All right, let's move on to the second problem. Right now, we're calculating the location of the nut in camera coordinates, and we want to get it in the base frame coordinates. To help us understand what's going on, let's mark the camera coordinate system and the base frame coordinate system on the board. The center of the base frame is right here. That's why all of these lines come right back to this point. When we attach the manipulator to the board, this dot is the point where the axis of rotation would go through. So when we attach the manipulator to the board, this is our x0 axis, and this right here, this is our y0 axis. In camera coordinates, the 0, 0 point is the upper left-hand corner of the screen. I'm going to see if I can find it. Right, the center of my camera coordinates is right about there. I'm going to try and put a dot there. Now, the x-axis in the camera moves along the top of the screen from left to right. This is the X camera axis. I'm going to try to draw that on my board. It's a little bit difficult to do because you have to draw while looking at the camera screen, not while looking at the board. But I'm going to try and do it. So the center of the 0, 0, the camera frame is up here. And then it goes like, there's another dot. And another dot. This is approximately my X in the camera frame, XC. It's upside down in my picture. Let me see if I can draw it right side up. There we go, that's XC. I'm going to try and draw the Y. There's the center right there. There we go. That axis is Y. I'm doing it upside down again. That's the Y of the camera frame. I know the position of the nut in the camera frame. That's what's printing out to my screen right now. I want to know what's the location of the nut, but expressed in the base frame in x0, y0. Now, there's an interesting function from way back in our kinematics study that we can use now to solve our problem. Suppose you have a homogeneous transformation matrix from one coordinate frame, M, to another, N. And suppose you know an XYZ point in frame N, and you want to know the location of that exact same point, but expressed in frame M instead. You can accomplish that by making a vector like this. X in the N frame, Y in the N frame, Z in the N frame, followed by a 1, and then multiply this vector by HMN. When you do that, the vector that you get out as a result will be the coordinates of that exact same point, but in the M frame, XM, YM, ZM, followed by a 1. This is referred to as coordinate transformation. So suppose that we could find the homogeneous transformation matrix from the 0 frame to the camera frame, H0C. Then we could multiply this matrix by the point that was found by the camera, and we'd get out the point in the manipulator base frame. Let's try it. We know that the homogeneous transformation matrix has two parts, a rotation matrix part and a displacement vector part. Let's do the rotation matrix part first. How could we rotate the 0 frame shown here? Let me erase this and draw it over here. This is our x0. So we have our x0, y0, and xc, yc axes. So how could we rotate the 0 frame to get it to match the camera frame? Let's start by dealing with the z-axis. In the base frame, the z-axis is pointing up, which you can tell by using the right-hand rule. But in the camera frame, the z-axis is pointing down. We could rotate the 0 frame 180 degrees around its x-axis to get the z0 axis to be pointing down. That would swap the direction of y0. And it would also swap the direction of z0. So after we do that 180 degree rotation around x, x0 is in the same direction as shown in my screen here, but y0 is pointing to the left. Now, how could we rotate this new 0 frame in order to get x0 to match xc? We could rotate around the new z-axis, which is pointing down. We would have to rotate a little bit more than 90 degrees, and the rotation would be in the negative direction, which you can tell by using the right-hand rule. If you put your thumb pointing down, you'll notice that the direction that we have to rotate x is against the direction that your fingers curl. We can use the protractor included in your kit to kind of estimate how many degrees additionally we need to rotate. So I'm going to start by lining up my protractor with the top of the screen. Then I'm going to look at what angle it is between these two things here. It's not very much. It's a little bit less than 5 degrees, maybe 4 degrees or something like that. So we could get the 0 frame to match the camera frame by first rotating 180 degrees around x and then rotating about -94 degrees around z. Let's write that rotation matrix. Next, let's find the displacement vector. The displacement vector is the displacement from the center of frame 0 to the center of the camera frame. The center of the 0 frame is right here, and the center of the camera frame is right up here. So the vector that we want is this one. I want to write that vector in the 0 frame. I'm going to take my ruler and try to line it up really well with the x0 axis. And the x0 axis is right along one of the printed lines. So I'm lining up the ruler with the printed line. Now I'm going to slide the ruler up so that the 0 point on the ruler lines up with the center of the 0 frame. What I'm trying to measure is the distance from here up to the center of the camera frame, which is up here, right there. So that's 1 centimeter, 1.5, 1.6, 7, about 1.8. And notice that that's actually in the negative x direction. So negative 1.8 in x. Let's see what it is in y. Once again, I'll try to line up my ruler with the pre-printed line, since that is my base frame coordinate system. I'll slide it over so that the 0 lines up with the 0 point on my board. And this is the distance that I want to measure from 0 to the edge of this screen. So it's less than 1 centimeter. In fact, it's less than half a centimeter. It's 0.1, 0.2, 0.3 centimeters in y, and again, that's in the negative direction, negative 0.3. Now the z part of the displacement will be 0 because z0 is defined as the surface of the board. So there's no displacement in z between the 0 frame and the camera frame. So now that we have both the rotation matrix and the displacement vector, we can go back and put these into our code. Let's stop the Python code from executing by hitting escape. The homogeneous transformation matrix isn't going to change as the code runs, so let's do the calculations up here at the top. Let's first calculate the rotation matrix. I'll split this up a little bit to make it easier to type into the code. Let's say that R0C is equal to NP dot, that is the dot product of two other matrices, a rotation of 180 degrees around X times a rotation of negative 94 degrees around Z, which I'll refer to here simply as RZ. Now let's put in those other two matrices up here. The rotation of 180 degrees around X is equal to, I'll make one set of square brackets for the whole matrix and then another set of square brackets for the first row. And the first row is 1, 0, 0. Then the second row is 0. The cosine, NP dot cosine of 180. But remember, we need to put this here in units of radians. So 180 is easy, that's just pi. Then the negative sign. And the last row is 0 sine cosine. Now let's do a rotation of negative 94 degrees around Z. To make this a little bit easier, let's convert negative 94 degrees into radians. Let's just call that variable rad. Okay, now we can use rad in this matrix. The first row is cosine, negative sine, 0. The second row is sine, cosine, 0. And the third row is 0, 0, 1. All right, so now we've got our R0C matrix. Let's put in our displacement vector, D0C. D0C is equal to negative 1.8, and that's all there is in the first row, negative 0.3 in the second row, and 0 in the third row. Okay, now we can use these things to fill out our homogeneous transformation matrix, H0C. Remember, we learned how to do this back in the kinematics section when we did homogeneous transformation matrices. So I won't re-explain it here, but we're going to use the concatenate function to put these matrices together. The first thing we want to concatenate together is R0C, and we want to concatenate that with D0C. And 1 is the axis along which we want to concatenate. That is the rows. Now we want to do another concatenation. What we already have for H0C, and we want to concatenate that along with the last row, which will be 0, 0, 0, 1. And the axis along which we want to concatenate is the column axis, so that's 0. If you want to review why we did this or how this works, go back to the section on homogeneous transformation matrices. Okay, now that we have the homogeneous transformation matrix, we can use it to find the location of an object, not in the camera frame, but in the base frame. Let's go down here. Let's create a vector that holds the XYZ location followed by a 1 in the camera frame. Let's call this P for point. The point in the camera frame is equal to a matrix where the first row is the X location, the second row is the Y location, the third row is the Z location, which is 0 because it's on the board, and the board is the 0 Z location. The last row is going to be 1. We always have to stick a 1 on the end of these points when we're going to be multiplying them times the homogeneous transformation matrix, because the homogeneous transformation matrix is 4 by 4. So we wouldn't be able to multiply it by a vector that only has 3 elements. So we stick the 1 on the end here in order to make it work. Okay, now the point in the 0 frame is equal to the dot product of H0C and PC. So the X location in the 0 frame is going to be P0, the very first element, which in Python is the 0th element. And the Y position in the 0 frame is going to be P0, the first element, which is actually the second element. So then what we want to print here, instead of being X location, Y location, is going to be X0, Y0. Let's test it. Okay, let's run this. Wait a bit for the background to stabilize, then hit escape. Now let's place the nut. It says the location of the nut is 3.75 in X and 5.3 or so in Y. Now that we're using base frame coordinates, we can tell if this is correct just by using the grid on the board. The X location in the base frame is 1, 2, 3, 4 in X. So we're off by about 0.2 in X, and the position in Y is 1, 2, 3, 4, 5. So we're off by about 0.2 in Y also, but 0.2 centimeters, that's pretty close to B for what we're doing. We can also improve the accuracy by tweaking our displacement vectors a tiny bit. Let me show you how to do that. I'm going to hit escape to exit this. Now, since we were off by 0.2 in X and Y, let's go back to this displacement vector. Let's change the X displacement by 0.2. Now, I'm not sure which direction is the right way to change it, so I'm going to start by making it smaller and let's see what happens. When the background is ready, hit escape. And now let's place the nut. This time it says our X position is almost exactly 4. And our X position is 1, 2, 3, almost exactly 4. So we've actually improved our accuracy. That was a good change. Let's see if we can fix the Y now also. It says we're at 5.2 and we're actually at 1, 2, 3, 4, 5 exactly. So I'll hit escape. And let's make this say 0.1. Again, I don't know if this is the right direction. We'll just test it. When the background's ready and nice and stationary, hit escape. And now let's place the nut. The Y says it's 5.3 and we're at 1, 2, 3, 4. Oops, I did the wrong direction. We're at 1, 2, 3, 4, 5. So I think we actually got a little bit worse. Let's go back and let's make this 0.5. And now let's run. The reason why we have to do this little calibration is because we're just drawing with a marker and measuring with a ruler. We can definitely be off by fractions of a centimeter with our measurements. Okay, let's place the nut. Now it says the X position is almost exactly 4. And it is 1, 2, 3, 4. And the Y position is almost exactly 5. And it is 1, 2, 3, 4, 5. So we are pretty accurate now. I think we're going to stick with this. So we've come a long ways here. We are now at the point where we can find the location of an object with a camera in the frame of our manipulator. And we've already learned how to get the end effector of our manipulator to go to an X, Y point. So the only part we haven't figured out yet is how to actually pick up the object. In the next unit of class, we're going to be learning how to control the position of our DC motor. We'll then hook up the DC motor to the rack and pinion device, which will actually execute the picking up operation.